Okay, let's go ahead and start. Thank you all for joining the AI seminar hosted through Matrix today. We have Dr. Amanda Fernandez from Computer Science, who's an assistant professor in the Department of Computer Science here at UTSA, and she's also a core faculty member in the Matrix AI Consortium. She's the PI for the Vision and Artificial Intelligence Lab at UTSA, and she has completed her doctoral work at University of Albany, SUNY in 2015, where her focus was on visual saliency estimation and generative learning models. Before joining UTSA, Dr. Fernandez was a research engineer with USAA labs and a private industry, and her interest was on computer vision and deep learning at that time. Her recent research interests are on adversarial learning models and computer vision, including robust media representations and applications in cybersecurity and physical sciences. Let's give a warm welcome to Dr. Fernandez.
Thank you so much.
Virtual claps.
Thank you, Darisha. I appreciate it. So yes, good morning, and thank you so much for having me this morning. I appreciate the opportunity, and I appreciate this really unique seminar series that Matrix has brought, and I'm excited to be a part of it. This morning, we'll talk about robust visual understanding through some semantic segmentation, saliency estimation, and overall, my goal is sort of to look into this computer vision research from the lens of deep learning. So we'll look at some challenges of deep learning research, how far we've come, and what kind of the state of the art looks like right now, March 2021. So we'll see how that goes. So from this high level understanding, we want to sort of look at how well can computer vision compete right now with the human visual system, essentially. You know, how good has it become, and you know, what are some of our challenges going forward? Not just how difficult are some of the things it's working on, but you know, where do we go from here? So we'll tackle some very difficult questions, but at a high level, I have a fundamental question. Why is it that we can put Nicolas Cage into the Matrix, but if I put this sticker next to a banana, it thinks it's a toaster? We have some very basic issues in computer vision still. And the fundamental causes for some of these, you know, are something that's a little bit difficult to kind of look at and solve. So we have some fundamental things to kind of take a look at. We'll look at adversarial examples. I really won't touch that much on deep fakes in this conversation. I feel like it's a whole nother topic in and of itself, but you know, we'll get there to some of the underlying technology. So for this talk, I'd like to focus on fundamental questions. How well can artificial intelligence actually understand visual data? And visual data in this case will mean images, video, pretty much any representation where we're learning something, you know, where we're looking from a camera's perspective or some faded. And then how generalizable is that understanding to different problems across different applications, across implementations, or really taking that algorithmic approach. And finally, how robust is that understanding? So overall, I need to make sure it's generalizable across data sets, but also what if someone tries to alter or unintentionally alters some of the data? And throughout answering some of these questions, I'll also incorporate some of the work that we do in my Vision AI lab, where we're sort of applying it to different fields, but I'll kind of go through this very quickly within the hour here, and we can get to some questions at the end. So let's look at together how well AI can actually understand data, how generalizable that understanding is, because they're kind of together, and then we'll get to the robustness a little later in the talk. So in trying to answer this, we can look at some of the state of the art in computer vision. We can see things like computer vision and deep learning models in particular being used for the Mars exploration very recently, sort of categorizing anomalies on Mars surface. We see Argonne National Lab, for example, using it for denoising and deblurring in some of their lensing systems. Recently, Timnit Gebru and her team kind of worked with Google Street View data And they were able to, just from street view data, driving around neighborhoods, reason about some of the demographic information, income, socioeconomic status, the voters, tendencies in some of those areas. And we're able to just, from images taken in neighborhoods, derive a lot of that information. And of course, we see a lot of medical applications where super resolution is incredibly helpful for MRIs in this example. But we also see super resolution for aerial imagery. We see it for virtual and augmented reality. We see it for lots of different types of applications. So computer vision and deep learning in particular is helping computer vision do some of these things better. And one of the things that we want to address is, how big some of these models have become and how deployable they are. And that's one of the themes that I'd like to talk about today. But in addition to just some of these classification-oriented things, we take in image data and we give back some prediction. There are also generative models making a significant impact today. And we see some of the generative examples in things like neural style transfer. So we see some really cool things computer vision can do with taking content of an image, applying some sort of style to it, and generating some sort of result where the content, the original content is there, but the style's been changed. And this is kind of where we see deep fakes evolve just a little bit, because over just the last, within the last decade or so, less than that, we've kind of seen generative faces get better and better to the point where they're very photorealistic. And what this does for us is this style understanding and this generative approach, not just predicting and inferring something, but generating something brand new, gets us to a whole new set of tools that deep learning can help us with in computer vision. So one example of this that I'd point out is generally when you see this kind of an image, you think segmentation. Or if you're in the computer vision space, you think we're labeling areas of this street. For example, here's a car and we'll label this as a road and we'll label this as a stoplight. But we can also, with generative deep learning models, flip that on its head. And we can start to draw this map first, a semantic map that says, I would like a curb here and a sidewalk. This pink area will be a sidewalk. This area will be the road. These red areas will be people. And we can use a generative model to create the scene that we're looking for. And some of that helps with being able to train some of those other classification type models. We can start generating our own data. But there's a host of different applications for this now where it's good to be able to kind of go back and forth. So at a very high level, computer vision's come a long way in the last 10, 15, 20 years. And just stepping back for a moment from the rush of new advances, how did we get here? How did we get to the point where I can generate a photorealistic-ish scene? If you look at this, you'll see some imperfections. But if you quick glance, you'd think that this was actually a photo taken of a street with cars on it. So how do we get here? We know probably a little bit, given this, this venue, about artificial intelligence. And you may be familiar with things like MNIST and how image processing sort of led into this area for computer vision, which led into deep learning. But let's walk through just a little bit very quickly. So in the 1980s, late 1980s kind of time frame, we're looking at being able to apply things like convolution to images to be able to reduce, or extract some relevant features from an image or from any kind of spatial data. So if we're inputting some sort of value, in this case, and at that time frame at Bell Labs, Jan LeCun and company were kind of looking at addressing the idea of handwritten envelopes and zip codes, and being able to automatically read the handwriting off of a piece of mail and digest that piece of information and pull the zip code off by default. And so if we have a handwritten digit of some sort, they looked at adding some sort of convolution. They came up with this idea of applying some of the kernels in a certain fashion. This idea of image processing had already existed. This idea of the kernels was already a thing, but kind of putting it together with this concept of condensing it down, pulling it afterwards to look at the features that had been extracted, and then adding this neural network. This in this case, just very basic few neurons that would kind of digest some of that information and then output some value. In this case, they're looking for digits 0 through 10. If this sounds familiar, about 10 years later, right, same group was sort of looking at doing this for chess, and out came the MNIST type data set. So there's a subset of NIST data set and something a little bit larger. And if you're new to the computer vision community, this MNIST data set is the hello world of computer vision. It is kind of handwritten digits with labels given, and this is what you might train your machine learning model on. And I say machine learning and not deep learning here because in this case, from this perspective, in this early approach, we're looking at literally creating some of these kernels and extracting some of these features ourselves. So we're not doing the deep learning where we're doing the feature extraction through the learning model. Instead, we'll create something like we have some sort of intentional image that we're applying it to. We'll manually create some of these kernels. And we might gather large libraries of these kernels together, and we can apply them for different purposes. So for example, we might form this kernel to blur an image. We may form this kernel to find certain directional edges. And this early approach was excellent at deriving some of that information. But those MNIST images were about 28 pixels by 28 pixels, very small. So we're looking at trying to scale those up, and this concept, which many others in the seminar series can speak far better than I, of this idea of maybe possibly brain-inspired computing, but looking at kind of modeling the brain and saying, is one layer, oh, the slides are stuck. I'm sorry. So excuse me for just a moment. Do you have, which slide number are you on?
7.
All right. So, well, the premise is that, we would like to, in the computer vision community, move into a situation where we don't have to define some of these kernels manually. And so ultimately would like to reflect how the human brain processes visual stimulation, maybe by taking in some of the early information, like some of these edges early on in a neural network, building up some layers, towards the end starting to recognize some higher level objects and some combinations of shapes, for example. And if we can emulate this process a little bit through using some of the convolution and some of the image processing techniques that we've learned about before, maybe we can start to process and understand data the same way that the human brain does very quickly. Now, this is the intention. We'll see kind of where this gets us a little bit. Over time, we'll see architecture sort of evolve, and especially through the data sets that we might be familiar with or seen, like MNIST and CFAR, that are very small. And data has grown over the last decade or so to incorporate more objects. And then finally, the ImageNet challenge that kind of ran from that 2010 to 2017 sort of time frame, where we're trying to identify certain object classes. We'll be given some sort of an image that's larger, maybe a 224 by 224 image, and try to identify maybe the top 5 results. So what item do I think it is? What category would I classify it as the most? And then what are the 4 other categories that I think would come next? So in terms of a value. You're probably familiar with this, but if not, that's pretty much what you need to know. What happened was over that time frame, over that 7-year period almost, we went from feature engineering and that manual feature extraction to having a huge impact with introduction of CNNs. One of those in the early years, maybe the 2012 kind of time frame, arguably with AlexNet, introducing some of the basics like the neural network processing, but also things like rectified linear units and different types of activation functions that help digest some of that information better. So over time, very quickly, convolutional neural networks had a huge impact on ImageNet until finally, in 2017, we're looking at 2.25% resolution or error rate, on that data set. So the question at that point became, is there an AI winter coming? Is this problem solved? Are we done, with this overall? And are we kind of waiting on this concept of computer vision is done, we can walk away and solve something else? And arguably, even though the models got deeper, the introduction of GoogleNet or Inception, the contribution there was essentially make something deeper. We can also make things more efficient. And solving it on one image data set doesn't necessarily solve it across others. And here's my example for this. If we're ever questioning, is computer vision or image processing essentially basically solved? The fundamental image that came out was this. So if we're trying to identify, for example, what's in this image, we'll take a look at it. And I would say it's a tree with goats in it somehow. So the context is a little different than what I would have expected, but I don't think, I'm pretty confident that's a tree with grass and goats. And if we look at some of the implementations, the current kind of built into the box for Microsoft Azure and Neural Talk, we'll see things like a flock of birds flying in the air, a group of giraffes standing next to a tree. The context throws it off, and there's some fundamental issues in convolutional learning that cause this problem. So we can take a little bit closer of a look at some of these. Before we do that, I just will kind of clarify where deep learning and computer vision kind of come from. There's a lot of myths out there that say things like deep learning is just machine learning, but deeper, right? And so that's how it learns better, which is not the case. Deep learning models are just black boxes. We don't understand them. They require massive amounts of data, and you can just dump any data that you want into there and it will tell you something relevant back, And then deep learning models, they're all very expensive. You have to have specialized GPUs to run anything at all, and you can't even try if you don't have the specialized equipment or you can pay for these cloud services. So there's a lot of this kind of going on, and it kind of affects some research sometimes as well. A couple of insights that we'll point out, and then I'll kind of refer back to in this talk at least, is there's a big difference between machine learning and deep learning in the idea of this manual or automatic feature extraction. And way beyond this, there are situations where more data in machine learning doesn't help you. You kind of get to a point where it plateaus. So there's a need for both machine learning and deep learning, and they're two very unique tools. So in no way, shape, or form is this ever one hammer for every nail. In terms of black boxes, there's explainable artificial intelligence research, and this is something really important to kind of take a look at. We should never be building a black box. We never want to just say, I stuffed something in, I don't know why I got the result back out. That's not art for research. Likewise, if we need massive amounts of data, that could be very problematic for real world applications. So I'll refer to some of our applications that we have where we're looking at few shot learning or sparsely annotated data, because annotating massive amounts of data is expensive as well. Even if you have it, it's hard to label it. I'll just say you can't just dump data into deep learning models. Data science is incredibly important. You need to analyze the data that you're just dumping into a model. You need to have an understanding of what you expect to get back out. The model itself has to be handcrafted. You can't just kind of take something off the shelf and expect it to work goals. But you can take things off the shelf and use them for their original intention in browser-based environments. You can use, framework-enabled components to do some basic image classification tasks, for example. They're pre-built, and we absolutely should take advantage of some of these. But we also want to take care to, just because we've solved a problem or we've created some sort of deep model, we want to get it closer to being able to be deployable as well. So we also look a little bit at embedded systems to understand why it might be important to be able to trim down your model as much as possible while preserving that accuracy. So let's look at some limitations in terms of computer vision. We know that it's tough to identify goats and trees, but how much more specific can we get? One open problem or limitation of current computer vision algorithms is this concept of cluttered scenes. ImageNet, the ImageNet challenge, some pretty clear images. So if it referred to a chair label, it showed us some pretty basic images of chairs that were easily identifiable. And the ObjectNet framework or ObjectNet dataset has recently been kind of put forth in the community to identify objects in different contexts or from different views. So for example, this chair is kind of sideways next to a bathtub. Or we might have a chair that's sort of sideways in a different location or next to another chair on top of a bed from a different angle looking down. T-shirts don't always appear in the situation, you know, that we expect. So maybe it's draped over a bed or crumpled up on a dresser. So being able to identify those objects is something that you and I as humans can do, but they're not explicitly expressed in that ImageNet or some of our usual base vision data sets. And if we use those vision data sets as a baseline, it can be very misleading to say, okay, we're fighting over 2.25% accuracy, whereas, you know, we're not actually at that point. So, I'm sorry, that was the error rate. If we look at the same models like AlexNet, VGG, ResNet, Inception, the ones that we had watched grow with ImageNet over the years, their performance is up here, this top dotted line, the top 5 or top 1 accuracy, and they drop significantly down to these 2 lines here, so top 1 and top 5 accuracy for this ObjectNet data set. And the point for this in the community sort of looking at, we can identify some of these items from very clear pictures, but what happens when they're in the real world and a chair is on its side or a t-shirt is on a bed instead of, you know, on a hanger or something along those lines. It's very difficult. We also need to look at real accuracy. So I want to test your human visual system very quickly. So what we'll do is we'll sort of take it from a CNN perspective. They're going to see an image for a very short period of time, and they'll identify what's inside of that image very quickly. And that's the only look that they'll get potentially at that one image. We may not actually use that again. In training, we might see it a few different times, but let's test and see how well you do on this. Okay, I'll show you an image very quickly and then I'll hide it again. Okay, here's the question. How many dogs were in that picture? You don't have to answer this, that's okay. But you have a number probably in mind. Only 1 dog in that picture. And these are kind of a unique subset of issues and problems that we run into in a lot of vision data sets that we would not have expected ahead of time. Mostly because if we were given these images originally, we would have labeled just the person in the image, and we would not have thought initially to label what initially very quickly looked like a dog, or worried about that in terms of our data set. We'd probably just categorize these images as people and then move on, right? And we kind of see this phenomenon happening all over, and people like to pull this out as it's happening in research data sets. So we get things like puppy or muffin, dachshund or bagel, kitten or ice cream, and you know, bird or guacamole. And this kind of happens. It's a recurring theme inside of some of these image data sets. So we can take problems and projects like the ObjectNet data set. We're just realizing that, you know, there's some data analytics that needs to go on to say, why are we performing so poorly on this image? Is it because it looks like a Chihuahua and that's why it keeps categorizing this muffin as a dog? Very important for us to kind of go back and look at this again. But this problem, as funny as it may seem, pointed to a larger issue in convolutional neural networks and points to something that fundamentally, you know, we need today. We need our convolutional neural networks to be a little bit different. We'll talk about the bias here in a minute, but the way we frame the problem is also important. So we're doing some basic image recognition from the standpoint of we have, you know, an image here. In this case, we're saying the probability of sheep, dogs, cats, and horses, for example. We can output this for image recognition. We can do object detection and identify localize where each one of those objects is. Even put a colored bounding box around the different objects. So each sheep gets a different color, for example. We could do semantic segmentation where we identify more specifically the pixel level location for each of those objects, for each of the classes that we're interested in. But instance segmentation gives us a little bit more information, actually separating these sheep. And that's a very different and very difficult type of problem. The definition between where this sheep ends and where this sheep begins is difficult. Not only that, but if I were to ask, for example, how did you identify this sheep back here? Is it because they have 2 legs? Because that's all we can see right now. It probably wasn't based on the fact that sheep have 4 legs and so on and so forth. We can't see that the sheep has a tail, or any of the sheep have tails. So there's identifying information that's difficult. If we're sort of relying on some of our CNNs for this, it can be difficult to extract a difference and draw some of these boundaries accurately. We're at the point where semantic segmentation is becoming more clear and more feasible, but this instance segmentation is very difficult too. Okay, so why are we facing this kind of a problem? Part of it is just because the way that our human visual system works is not quite that convolutional neural network approach. We don't have this idea where we're scanning, an image over with some kernels and deciding what information is in there. So if I were to pass, for example, this image, which admittedly is weird, into a CNN, it wouldn't tell me that it's a picture of a dog with a weird texture on it, which you and I would probably identify as see a Labrador in this image. Maybe you don't, or you see a little bit different, but chances are that that high level view is this Labrador type of thing. And so all of this sort of tells us that convolutional neural networks, even though they've been revolutionizing computer vision for 10 years, they're very sensitive to just texture in the image. They have some really ingrained biases that it learns from your training data, but also is sort of built in fundamentally into that architecture. And that means that your learning is just going to be human learning. Human learning, if I were to show you, for example, a picture of a brand new animal you've never seen before, you probably wouldn't think it's fork, right? Even though it has certain texture, it's in a certain context or something, it's very difficult it's very easy for you to think it's a new animal not seen before, as opposed to let me to categorize it as something in sort of a context. So CNNs have these difficulties, and these are that we're grasping with in recent days. But another concept is that our data that we're passing in, not just in the computer vision community, but in deep learning, is not generally Euclidean. We don't all have this really straightforward set of data structure. Might have difference of molecules, for example, or we have a tree presentation, something. And even right now, there are ways still with some of this, it's not always the easiest thing to pass in an entire network into a network. There are sort of ways around, and convolutional networks trying to do this. As a research community is one of the open problems. How can we best represent some of this? Taking that tree, smushing down into the representation that we're used to seeing.
Is this microphone better?
Very good.
Great, okay. Let's see. Perfect. So in order to address some of these issues that we have in computer vision with CNNs, there are new approaches that we need to take. There are plenty of approaches that we can take and have been taken in the data analytics community, making sure that our data is as relevant as possible. But we need to approach our architectures a little bit differently as well. One way that's been proposed very recently, just last year, is to sort of draw from the natural language processing community. Use this concept of transformers, leverage fundamentals in BERT. If you're familiar with NLP in that community, BERT is kind of enabling things like transformers and a transformed input of sorts, and we can translate that into the vision community by sort of taking blocks of our image and taking this global perspective of an image rather than kind of a sliding window where we get a little bit more myopic in a CNN. And the hope here is that if we're incorporating the data in not just superpixels, but larger patches within an image, and we're using attention mechanisms in there, then we can start to identify what's most important in an image and improve some of our classification and eventually even some of our generation. And you know, this concept isn't new to image processing. The idea of attention has been there for quite a while, especially you know, from the standpoint of determining what's most salient in an image. If I was given this type of image, for example, and I wanted to address or pull out the most relevant information or what the human visual system attends to the most, we would probably choose the fish, and that seems from this example from a known data set, watching the fixation points from human observers, we'd aim to generate this type of a map that indicates where to remove some of the information and what information to keep, so that ideally we can just extract the most relevant information and then process this image as needed. So I might just need, for example, the fish. So depending on the problem that we're trying to solve, incorporating this concept of attention into our architectures is incredibly important. We want to make sure that we're attending to the right things. And so I'll kind of point out some of the applications as I talk about some of these architectures and implementations. But one application that we've been looking at in our lab is in terms of eye tracking for VR and AR. And one reason that eye tracking is so important and being able to kind of watch the user is so that we can they can leverage this for foveated rendering. So if I can watch your eye and I can see where your pupil's located, you know, where you're looking from 1 second to the next, we can render exactly where you're looking in the highest resolution possible, and then gradually less resolution until ultimately in your peripheral vision, it's sort of blurry. And what that does is enable us to create some very significant algorithms that are cheap. We don't have to render, you know, everything at such a high quality outside, which saves us a lot of computational power. And we're really just kind of focused on rendering this as clearly as possible. It can also run very fast. So we're kind of, in this case in our lab, we're sort of focused on how do we locate the eye if we're looking at the user, you know, while they're wearing some of these VR, AR headsets. Can I identify as closely as possible, given some sort of labeled ground truth, very accurately those regions of the eye? And so we want to do it accurately. We want to do it as cheaply as possible, make sure that our models are as small as possible, and also ensure that you know, it's as you know, clear in the end. And this comes with its own issues. But ultimately, this does require still some labeling. So even though we're doing deep learning, we're not you know, we're not doing any of the manual feature extraction. We still need a significant amount of data sometimes, and that data is expensive to get. You have to hook somebody up with the augmented reality eye tracker, label a lot of these data points. And so shortly thereafter as well, we're looking at implementations where we have maybe less labels for some of those, but just looking at it from the perspective of, you know, how well can we do in comparison with, you know, existing out of the box type of implementations. We might look at, you know, for example, we use an encoder decoder type framework for that balance of just accuracy and efficiency, assuming that we have all the data that we need to be able to build. We can intentionally build some of our neural networks, and it's not that we're not making them deeper. We can make them very deep with entire areas. For example, a bottleneck consists of a smaller subset of layers. But each one of those bottlenecks, we can incorporate things that do reduce the computational time and requirements a little bit. So we can incorporate things like regularization and dropout. We can dilate our convolutions so that we're clarifying things just a little bit better and making the computations smaller. But ultimately, if we want to incorporate that idea of sparsely annotated data, where maybe, for example, instead of labeling each item in a training set independently, we can just label the start of a session. So the user puts on their mask, that first series or sequence is kind of labeled, and after that, it's up to your machine learning or deep learning algorithm to kind of determine when the user is, you know, where they're looking, and kind of create your own ground truth essentially during that training process. And for that, we can take a similar approach, but in all cases, we're sort of looking at this encoder decoder type of framework. We still want to balance the model complexity, the speed and accuracy with this lack of data or lack of set data. And we'll keep track of this by identifying how well it does on each one of the categories. So the background around the eye and the iris and the pupil, how large our neural network is in terms of the number of trainable parameters. So we're interested in how many trainable parameters, because that adds time and it adds, you know, computational resource requirements. And overall, these numbers are kind of calculated as this mean intersection over union, which is an area that's most important for semantic segmentation. We also have some applications in autonomous driving. For the sake of time, I'll sort of kind of bypass these, but as the images get larger and as your scenes get more complex, this requirement of accuracy, balance, and you know, efficiency and the size of your model only grows. It gets, you know, increasingly more complex as the time goes on. We also have applications for this same reason. If we can solve this for some basic problems in VR, AR, for example, and then we can try it out on bigger problems like autonomous driving, we can take these to application areas that don't have a ground truth data set and may not necessarily have a known answer or response that's easy to access. And so one of those is we've paired up with the Connect Consortium to be able to do some analysis with non-traditional data formats on nuclear fuel materials generation and fabrication. So when we're looking at some of the data, we might be looking at traditional, you know, Euclidean type data. We might be interested in some of the images that are being passed in, and applying some of this segmentation while watching some of the fabrication of the fuel forms. And what that does is we don't necessarily know what the right answer is, but if we've proven it elsewhere, we can not quite transfer learning, but we can reutilize what we know about our architectures that does work. But at this point, we're sort of still looking at those CNNs, and we'll kind of start to implement and incorporate some of those other architectures and the transformers, for example, and see how well that kind of brings us to a better understanding of the visual data. So in this last 10 minutes or so, I'd just like to talk about how robust that understanding can be from the perspective of, yes, we're using CNNs, and our visual system for computer vision may be a little bit limited or having some of these kind of openings. And so if we have some sort of noisy input, intentional or not, how robust can we maintain that accuracy? So to this point, we've sort of talked about how computer vision is trying to automate some of those tasks or emulate the human visual system as much as possible. We're identifying some of the patterns and structures that are within an image, focusing on important data. The question is, what happens if that input's attacked? So I like this image because it plays a little bit of a trick on your brain that emulates what adversarial examples or noisy inputs can do. So if you take a look at this image, it kind of looks like a spiral. But if you were to focus on it and maybe cover part of it with your hand, you'll notice that they're actually concentric circles. So even though your brain, because of the orientation of the squares, it kind of wants you to think it's a spiral, it's something else. And this is sort of a little bit leaning back towards that puppy or muffin issue, where our visual system can be tricked if it's a certain short period of time, or the data is just lined up a certain way, or honestly, we don't see well in the dark, right? And so or very, very far away. So maybe the way that we've come to emulate the human visual system should be revised, and that's kind of the ongoing research here. If we're attacked intentionally, that's where we want to make sure that we're as robust as possible as well. So our adversarial attacks are one of the common areas that you may have encountered, especially in cybersecurity or applications. Here's an example that we generally see quite a bit. We would have an image, our traditional model like Inception or VGG might classify this with a confidence of 92% that this is a fish. If we add some noise to it strategically, and I'll be less vague here in a moment, ultimately the goal is to visually leave the image the same, but to get that classifier to think it's something else, like a boat, for example, with a high confidence value or something close. So we've probably seen this. You might have heard of adversarial attacks also in person. May have seen this example as well, where we might initially identify this stop sign as a stop sign for autonomous driving purposes, but if we stick a few strategically engineered stickers or literal stickers on the stop sign outside, we can fool some of these same image processing algorithms into thinking that this is a speed limit sign, for example. And so this can be extremely problematic in the autonomous driving perspective, because this stop sign does not look that altered to you and I. If I were driving around, I would still know this is a stop sign and I would stop. If I would think the autonomous vehicle would kind of think the same thing, but in this case, it's been tampered with. And so it's not only very meticulous patches that have been successful. Tencent also, just a couple of years ago now, showed that Post-it notes, 3 Post-it notes on a highway were able to move or change lanes for Tesla's system at that time. So get the autopilot to move into a different lane or off the highway by strategically placing at different cadence a few very basic things that aren't even engineered. They're just in the right place at the right time. That can be very problematic. And finally, there are some folks in CMU that were able to just print from a silhouette of eyeglasses. These are regular Epson printer, to print out some noise, tape it to glasses, and make themselves invisible to TSA security cameras. Security cameras were looking for people, and when it encountered the noise, this kind of tortoiseshell looking noise on the glasses, it reflected as something else. So they're looking at kind of hiding in plain sight, basically. Obviously a discussion that they had with security beforehand, but very important for us to kind of keep an eye on, because if we were to see these adversarial attacks in person, we would think very little of them. I would not imagine that these stickers on the stop sign would do anything to a vehicle, or Post-it notes on a highway. I would just think it's littered. So it's something where there's a fundamental flaw in our computer vision systems we need to keep an eye on. And part of that flaw has to do with this, the gradient basis of a lot of training models and how our CNNs are built. So the initial paper that kind of looks into this, it looks at the fast gradient sign method, and FGSM has been a successful gradient-based attack for a few years now, and it's one of the ones that we still look back on, where we're engineering that noise that I kind of glazed over earlier as the loss with respect to the input image. And so we're taking in that, we're using the loss that was used in terms of training and understanding our images better, and we're kind of reversing the gradient and making a change to it. And this numeric value here is our epsilon that we can change and factor just a little bit to dial up or dial down the noise level. And that will also correlate a little bit to how visually relevant some of those changes are. So whether or not you and I as humans actually see some of those changes. So changing that epsilon, for example, maybe you have this input, an initial Labrador at 41% confidence. If we up the epsilon and we start to attack 0.01, we'll have not a lot of visual change between these two images, but we're fairly confident it's no longer a Labrador Retriever. So we made a significant change. If you dial up the epsilon too far, we can start to see some of that change as well. And what this gets to is the fact that our CNN algorithms are generally trained and they're learning with gradient descent, and that's a flaw fundamentally inside of the learning mechanism. So we don't have a ton of time, but in terms of attacking the state of the art, there are some cybersecurity concerns like giving access to the model, being able to actually open access to the model and having somebody input some values will give you back information that you need in order to attack it. If you use some of these backbone CNN models, these really popular ones like VGG and Inception that are out of the box in their frameworks, that's going to increase your susceptibility to these types of attacks. Because when you're trying to attack something, transferability is going to be very important. You can identify what model you want to, you can create your own substitute model, attack your substitute model, and then try those same attacks out on something else. So if we want to build more robust models from a high level, we can do some basic things like transform our inputs. We can make some changes in terms of not using the same data set, not just using ImageNet to train our architectures, because if that's known, then an attacker can go ahead and make a change that they know will affect the ImageNet dataset training, or not using the same architecture right out of the box, because no matter what training data you use, if it's that same architecture, that can also be attacked. So that means kind of creating your own training data, maybe doing some adversarial training, but we can watermark by putting a backdoor into our system. But ultimately, most of these get to obfuscating the gradient of some sort, making it so that even though you use gradient descent to learn, you're obfuscating it in some way by either manipulating the input within the architecture or beforehand. And the community is sort of looking at this as just, we shouldn't be doing gradient descent. It's not helping us, to continue to use CNNs in all applications. They're great for some things, but not for others. And in addition, the robustness isn't there. We have some bigger issues to overcome. So some of the research that we've been looking at aims to apply that attention mechanism, maybe by identifying important or attentive areas within an image. This is hard because the puppy's the whole image, so he gets all of the attention. But if it were zoomed out, we'd be able to see kind of a higher level where only the attended area is where we should be maybe removing some of that noise, removing some of the attack. And so we've kind of looked at this across different attacks, FGSM, Deep Fool, DPA, and others that have kind of come out. And also looking at some of those transformations within the neural network to use some attention, to use some of the same autoencoders, but in an adversarial setting to be able to make some changes there. So I'm a little bit out of time. I'll just kind of point out that we were looking at for computer vision, deep learning, our lab as a whole aims to kind of understand how well AI understands this visual data. We look at how generalizable that might be and how well it can be fooled, so that we're building robust computer vision systems built with deep learning architectures. And this is us in NPB. So thank you so much. I'll open it up for questions here. All right, so there's a question in the architecture you presented on slide 19. What is the main idea of using the encoder decoder sections? Let me see. Subsections. Are you using that pair with one specific goal is that model used as a supervised or semi-supervised? So that's a great question. So we can utilize, this is kind of reflective of ENet. So we call this mini ENet. The ENet architecture also similar to kind of a UNet architecture that had come and they've sort of evolved over time. But this concept of encoder decoder, the idea here is that we can kind of reduce down the size of our image, reduce down some of the processing. What that does for us is save in terms of computations and efficiency and the size of our model. But in addition to that, each one of these levels is a smaller bottleneck here, and the strategy here is to be able to split the input to a series of convolutions, which we would have had if it was just a series of convolutional layers, but also simultaneously take it out into pooling and we'll use the padding just to be able to get to things, but we can pool and convolve at the same time and then recombine them on the way back out. And what that does for us is getting a little bit finer of a definition around some of these areas. So one of our studies, for example, this is the ground truth at the known label for this image. This is the representation from a just dilated CNN. We're using a convolutional neural network with some dilation in there to reduce the size overall of some of the computations. That's one really good strategy for retaining accuracy, but removing some of the computation required and some of those, keeping things a little bit smaller and quicker. But you can see where the edges are blurry, some of the areas are morphed. And so we need some of this extra, we need a little bit more convolution. We need a few more convolutional layers, but we can pool in the meantime to be able to take sub areas like this and reduce into some of the more specific pixel representations for like the top of the eye here, for these areas that are kind of hanging out over here. That answers your question. Yeah, so a residual network can definitely be used in some of these cases as well. We can showcase residual networks in comparison. There are a few studies in the area that we're also looking at just using a different, a different type of architecture. I think transformers are going to be kind of the way to go from the standpoint of we need that attention mechanism to be able to see, where the most relevant data is going to be. There's a lot of issues with some of the residual networks, for example, picking up on other areas that might be interesting, but we would not attend to as human observers. So the eyebrows, for example, are a little bit distracting. Two questions from Mertuza. Most of the progress in deep learning you described focused on just image data. How much progress is made on interpreting multimodal data such as videos? So that's a great question. In terms of there's a significant amount of research focused on this multimodal concept, video with audio, from my, again, very myopic perspective of looking from the computer vision community with deep learning. I've seen a significant improvement utilizing that audio input as well from a spatial perspective and applying some of the same techniques that we would have seen on the image frame by frame within a video or on the audio taken as an image, essentially, and processed the same way. So all of the same tricks that we're using on the images have been applied back to the audio. I'm sure in the general signal processing community, there's significant leaps and bounds being made in the audio. And my thought is right now they're kind of being combined for some of that deep fake detection. That's one of the big areas and sort of applications there. We're sort of very funneled into the deep learning computer vision space, but model explanations are also good to make models more transparent. However, explanations can also give away information. Exactly. So if we have explainable models, we kind of give away the information about training data, train the models, how much progress has been made in the direction of privacy of explanation techniques. So that's a great question as well. I'll actually refer back in ICML 2018, there's a paper called Obfuscated Gradients by a few of the folks that are kind of high level or most focused on adversarial attacks. One of the takeaways from that paper was just that at some point in time, you have to accept that a lot of these, this artificial intelligence and this network will be white box. So instead of trying to engineer this situation where you're not going to tell anybody how your model is built, because in doing so, you potentially aren't telling yourself, it's become a black box again. Rather than get away from explainable AI, we should focus on defenses and kind of anticipate any attacks where the attacker is going to know everything about your model. Maybe they don't know about your proprietary data training set, but they're going to understand or be able to figure out some components of your neural network. And so from the vision community, that's where we're kind of focused. And that's actually why this has become a security issue for the vision community. We want explainable AI. We want to be able to kind of explain what our neural network's doing. So we don't want to, hide any of that information. But I think progress is kind of being made from that perspective. Another question, have you considered using the semantics of the scene to determine salience rather than basic image properties, or is it feasible? Sure, so the couch on the road is salient because it doesn't belong there. Absolutely, and so that's actually what's, this idea of the couch in the road type thing is what's problematic for our CNNs these days as well. So the couch in the road type of example that's relevant. It's not something that I would have trained an autonomous driving categorization on. So it's important for me to use a deep learning model at this point because my machine learning model may only have a certain number of categories. But my deep learning model may not be used to seeing it because it's unusual. And it's important because I need to know that it's not drivable. I can't drive over the couch. But using the semantics of the scene and the context has misled us a little bit in some cases. That's an open problem for CNNs. Even in this picture of the dog, there's no context here that tells me that it's a dog, and for that reason, it sort of misleads it a little bit. If I were to take this image and put it somewhere else, like in a park, it might give it a little bit more of an indication that it's a dog. So in some cases, context is important. In other cases, like the cluttered object recognition or ObjectNet, it becomes difficult because t-shirts can be on a dresser or on a chair, or chairs can be upside down. So we kind of have to use context strategically. Oh, okay. So if there aren't any other questions, that's okay. Well, it seems like we have a couple of technical difficulties this morning, but if there are any other questions, I can stick around for a few more minutes, but essentially this is what we have in terms of robust understanding. I really appreciate this opportunity to come talk to you guys and the series overall. Thank you so much for having me.